Lesson 19, Reflection. Reflection is the bouncing back of a wave without absorbing its energy. Mirrors are excellent reflectors of light waves. In this lesson, we're going to be studying two types of mirrors: plane mirrors and spherical mirrors. In spherical mirrors, there are two types, concave and convex. Plane mirrors are flat mirrors that reflect light at the same angle it hits the surface with. Concave mirrors are mirrors that curve inward. We can remember that they curve inward because they're concave, like a cave. Concave mirrors are also called converging mirrors. Convex mirrors are mirrors that bulge outward. They're also called diverging mirrors. The images you see in convex mirrors are always smaller and inverted, which means that they're always upside down. Part 1. Plane mirrors. Plane mirrors are flat mirrors. The normal line for a plane mirror is a line we can draw on our diagram perpendicular to the mirror, located where the light ray hits the mirror surface. This is our normal line. The angle of incidence is the angle between the incident ray, the ray that hits the mirror, and the normal line. This is our angle of incidence, which we call theta I. The angle of reflection is the angle between the reflected light ray and the normal line. So the incident light ray hits the mirror and is reflected off at an angle, and theta R is the angle of reflection, the angle between the reflected ray and the normal line. The law of reflection for plane mirrors says the angle of incidence is equal to the angle of reflection. Theta I must equal theta R. If a bundle of parallel rays strike a smooth surface, or a plane mirror, they all obey the law of reflection and emerge as reflected parallel rays. This is an example of specular reflection. Smooth water surface on a sunny day is an example of this kind of specular reflection. When parallel rays strike an irregular or rough surface, they will not be reflected as parallel rays. In each case, the ray obeys the law of reflection, but the rays are reflected in a multitude of directions. The surface is said to produce diffuse reflection. A wavy water surface on an uncalm day is an example of diffuse reflection. Example: what is the angle of reflection for the light ray in the diagram below? The first thing you need to do is draw the normal line onto the diagram and determine what theta I is. Theta I is the angle between the normal line and the incident ray. This is equal to 70 degrees because 70 plus 20 makes 90, and the normal line is perpendicular to the mirror surface. The law of reflection says the angle of incidence must equal the angle of reflection, so the angle of reflection must also equal 70 degrees. Example: what is the angle of reflection for the light ray bouncing off mirror 2 in the diagram below? Step 1 is to draw the normal line for the first mirror. Our normal line is perpendicular to mirror 1. The angle of incidence is the angle between the incident ray and the normal line. In this case, this is 60 degrees, because 60 degrees plus 30 degrees makes 90. The ray reflects off mirror 1, and the angle of reflection is equal to the angle of incidence, which is 60 degrees, which makes this 30 degrees. We now have a triangle with angles 30 degrees and 100 degrees. We know a triangle must add up to equal 180 degrees. This means the third angle in our triangle must be 180 minus 100 minus 30 is 50 degrees. So this angle here is 50 degrees. We can now draw the normal line for the second reflected ray. We know the angle between the normal line and plane mirror is 90 degrees, so the angle between the incident ray on mirror 2 and the normal line must be 40 degrees, because 50 plus 40 makes 90. The reflected ray off mirror 2 is reflected at the same angle it was incident on mirror 2 with, so it's reflected at 40 degrees. This means the reflected angle off mirror 2 is 40 degrees. Part 2. Spherical mirrors. Spherical mirrors are mirrors that have the shape of a piece cut out of a spherical surface. Concave mirrors are the inside of the sphere. Convex mirrors are the outside of the sphere. Before we can solve problems with spherical mirrors, you need to know some spherical mirror vocabulary. The center is the center point for the sphere that forms the mirror. We label this with a C. The principal axis, or PA, is the line that cuts through the center of the mirror. The vertex, we label this with a V, is the point where the principal axis intersects with the mirror surface. We call something real if it's in front of the mirror, or it exists in the real world. We call something virtual if it exists only inside the mirror and doesn't appear on the side of the mirror that's in front of the mirror. A concave mirror is also referred to as a converging mirror. This is because any ray that hits the mirror parallel to the principal axis will converge on the same point. We call this point the focus. Let's draw it into our diagram. Any ray that comes in parallel to the principal axis will reflect from the mirror through a particular point we call the focus. It doesn't matter where the parallel line comes from. If it's parallel to the principal axis, it will reflect through the focus. In fact, the focus is called focus because it's the point where all the light will focus towards. A concave mirror has a real focus. The focus exists at a point outside the mirror in the real world. The focus is also related to the location of the center. The focus is halfway between the vertex and the center, which means focus is equal to 1/2 of the center. A convex mirror is also referred to as a diverging mirror. This is because any ray that hits the mirror parallel to the principal axis will diverge from the same point. We call this point the focus. Let's draw this into our diagram. Any ray that comes into the mirror parallel to the principal axis will reflect from the focus out of the mirror. It doesn't matter where the parallel ray comes from, it will reflect from the same point from a location somewhere inside the mirror. Because the light is all diverging away from each other as it reflects off the mirror, this is why we call it a diverging mirror. The focus is inside the mirror for a convex mirror. This means it's a virtual focus. The focus for a convex mirror is also equal to 1/2 the center value. There's also some vocabulary we can use for the characteristics of images. The orientation of the image, the size of the image, and the type of image. An image might be either upright or inverted in its orientation. It could be bigger or magnified, or smaller, which means you can see a much larger area in the mirror. You could have a virtual image, which is an image that appears to be inside the mirror, or a real image, which means that the image is focused in a location in front of the mirror, and it appears to be in front of the mirror. If you memorize the following image attributes for concave and convex mirrors, you'll find solving problems involving spherical mirrors much simpler. We'll start with concave mirrors because they have much more complicated image attributes to memorize. For an object that's placed beyond C, the image will be smaller, inverted, and real. We write this as SIR, smaller, inverted, and real. If you place an object at C at the center point for the spherical mirror, the image will be inverted in front of the mirror, but the same size as the object itself. NIR, no change in size, inverted, and real. If you place an object between C and the focus, you will end up with a larger image, inverted, on the real side of the mirror. BIR, as in bigger, inverted, and real. If you place an object at the focus for a concave mirror, you will see no image at all. You'll just see a big blur. No image. And if you place the object between the focus and the vertex of the mirror, you will have an upright image that is bigger but inside the mirror, which means it's virtual. Or LUV, love, larger, upright, and virtual. So memorize SIR, NIR, BIR, no, love for a concave mirror. For a convex mirror, the image will always be the same, SUV, smaller, upright, and virtual. Ray diagrams. You can sketch the relative location and size of an image in a mirror using a ray diagram. To draw a ray diagram, you use a ruler to sketch 3 rays from a single point on the object in front of the mirror. The first ray comes in through the focus and reflects parallel to the principal axis. The second ray you draw comes in parallel to the principal axis and reflects through the focus. The third ray you draw comes in through the center and reflects back through the center. The image is the intersection of the 3 reflected rays. We're going to run through quite a few examples to help you understand ray diagrams. The first will be for an object placed beyond C in front of a concave mirror. The arrow in the diagram is the object in front of the mirror. We'll start by making a prediction. We have SIR, NIR, BIR, no, love for a concave mirror. Since the object is beyond C, we predict SIR, which is smaller, inverted, and real image. We draw our 3 lines. The first line is a line that comes through the focus, hits the mirror, and reflects back parallel to the principal axis. The solid line is the incident ray. The dotted line is the reflected ray. The second line comes in parallel to the principal axis and reflects through the focus. The third line comes from the object through the center, hits the mirror, and reflects back through the center. We can now draw a little arrow pointing at the intersection of our 3 reflected rays. This arrow is smaller, inverted, and since it's on the real side of the mirror, it's also real. Next example is placing an object at C. We would predict that this is going to be NIR, no change, inverted, and real. We draw our first ray coming from the top of the object through the focus and hitting the mirror. It reflects parallel to the principal axis. The second line comes parallel to the principal axis and reflects through the focus. Since the object is at center, the line coming from the object through center doesn't actually hit the mirror. But we can draw the reflected image pointing at the intersection of our reflected rays, and we see that there's no change in size. It's the same size as the object, it's inverted, and it's on the real side of the mirror, just as we predicted. Next, we have an object placed between C and F. We expect this to be BIR, bigger, inverted, and real. We draw our 3 lines. The first line comes from the top of the object through the focus and hits the mirror. It reflects back parallel to the principal axis. The second line comes in parallel to the principal axis and reflects back through the focus. The third line comes from the center through the top of the object, hits the mirror, and reflects back through the center. We can draw the image pointing at the intersection between our 3 reflected lines, and we see that it's bigger, inverted, and on the real side of the mirror, just as we predicted. If you place an object at F, we predict that there should be no image formed. We'll draw our 3 lines to confirm this. The first is a line that comes through the focus to the top of the image. Since the object is at the focus, this line never hits the mirror. The second line comes parallel to the principal axis and reflects through the focus. The second line comes through center, hits the mirror, and reflects back. These 2 reflected rays are parallel. They will never intersect. And because there's never an intersection between the reflected rays, there's no image formed. It's just a blur. Our final concave mirror example is an object placed between F and the vertex. We expect this to be love, larger, upright, and virtual. Our first ray comes through the focus to the top of the image and hits the mirror and reflects back parallel. Our second ray comes in parallel to the principal axis and reflects through the focus. Our third ray comes through the center, hits the top of the object, and hits the mirror, and reflects back in the direction it came from. You can see that there is no reflection on the real side of the mirror. But if we follow these 3 lines back into the virtual side of the mirror, we find an intersection point. And we can draw our image pointing at this intersection point, and we see that it is larger, upright, and virtual, just as we predicted. For a convex mirror, there's only one kind of image formed: SUV, smaller, upright, and virtual. We draw our first ray pointing through F at the top of the image. Since F is inside the mirror, we point it from the object to the focus. This ray reflects back parallel to the principal axis. We continue the dotted line of the reflection into the mirror because we predict it's going to be a virtual image, and the intersection will be inside the mirror. The second line comes in parallel to the principal axis and reflects from the focus. The third line comes from the center to the top of the object, but the center is inside the mirror, so we point from the object to the center. This reflected line reflects in the same direction it came from, so it reflects from the center. The intersection of our 3 lines inside the mirror is smaller, upright, and since it's on the virtual side of the mirror, it's a virtual image as well. Part 3, the spherical mirror formulas. There are 2 equations we can use to solve for the image attributes of a spherical mirror. The first equation is 1 over F equals 1 over dO plus 1 over di. I'll explain what F, dO, and di are in a minute. The second equation is M equals HI over HO also equals negative di over dO. dO is the distance from the actual object to the vertex of the mirror. Since it's always on the real side of the mirror, it's always positive. dO will never be negative. di is the distance from the image to the vertex. It's positive if it's a real image. It's negative if it's a virtual image. HO is the height of the object, measured from the principal axis. Since the object is always upright from its perspective, it's always going to be a positive number. You will never have a negative HO. HI is the height of the image. This is measured from the principal axis. If the image is upright, it will be a positive number for HI. If it is inverted or upside down, you will have a negative number for HI. F is the distance from the focus to the vertex. It's positive if it's a real focus. This means it's a concave mirror or a converging mirror. It's negative if it's a virtual focus, which is what we find in a convex mirror or a diverging mirror. And don't forget, the focus is equal to 1/2 the distance to the center. M is the magnification. The magnification is positive if it's an upright image, it will be a negative value if it's an inverted image. If the magnification is greater than 1, you have a bigger image. If the magnification equals 1, you have a same size as the object image. If the magnification is less than 1, you have a smaller image. These equations are best understood through some examples. First example, a 5 centimeter tall object located 40 centimeters from a mirror produces an inverted image that is 2 centimeters tall. What is the focal length of the mirror? Before we solve these curved mirror questions, it's best to make a prediction. We know the possible image attributes for a curved mirror are Sir, Ner, Bur, No, Love if it's a concave mirror, and SUV if it's a convex mirror. Since it's an inverted image, we know it has to be either Sir, Ner, or Bur. This means that the image has to be inverted, but it also has to be real, since there are no inverted virtual images. We also know it has to be a concave mirror, so we expect to have a positive focus. This means that we expect DI to be positive, because we have a real image. We would expect HI to be negative, since we have an inverted image. And we'd expect F to be positive. Now let's do the calculations. We are given the distance for the object equals 40 centimeters. The height of the object is 5 centimeters. The height of the image is 2 centimeters, but since it's an inverted image, this is a negative value. To solve for the focus, the only equation that has focus in it is the first equation, 1 over F equals 1 over DI plus 1 over DO. In order to solve for the focus, we need to first solve for DI. We can use the second equation to do that. The second equation is M equals negative DI over DO equals HI over HO. This is actually like 3 equations in one, so we only take the part of it that we need to solve for what we have. We don't need the M part, since what we need to find is DI. Rearranging this for DI, we get DI equals negative HI DO over HO. This is negative times -2, because our HI is negative because of the inverted, times 40 for our DO, divided by 5 for our HO, which gives us a distance for the image equals plus 16 centimeters. This is, as we predicted, real because of the positive answer. So we now know our DI is equal to 16 centimeters. We can solve for F using 1 over F equals 1 over DI plus 1 over DO. Another way of writing this is F to the -1 equals DI to the -1 plus DO to the -1. We can rearrange for F by inverting the opposite side. This is DI to the -1 plus DO to the -1, all to the -1. So F equals 16 to the -1 plus 40 to the -1, all to the power of -1, which gives us a focus equal to 11.4. This is positive, which means we have a real focus, which means we have a concave mirror like we predicted. We make these predictions so we can check that our answers are accurate at the end. Here's our second example. A 12-centimeter object is placed 25 centimeters from a convex mirror with a focal length of 7.5 centimeters. How tall is the image? We start with some predictions. Since this is a convex mirror, that means we can eliminate most of the possibilities, and all that's left is SUV. The image will have to be smaller, upright, and virtual, which means we expect HI to be less than HO because it's smaller. Since it's upright, we expect HI to be a positive value. And since it's virtual, we would expect DI to be a negative value. Since it's a convex mirror, it's important to realize that this focal length must be negative because convex mirrors have virtual focuses. Next, we'll do some calculations. We are given the height of the object, HO, equals 12 centimeters. We're given the distance of the object to the vertex, which is 25 centimeters. And we're given the focal length of this convex mirror, and since it's a convex mirror, we know it's a negative focal length, so that's negative 7.5 centimeters. We're trying to find HI. The formula that we could use to find HI is the second one. We would use HI over HO equals negative DI over DO. But we don't know DI, which means our first step is to use the first formula to find DI. The first formula is 1 over focus equals 1 over DO plus 1 over DI. This is focus to the -1 equals DO to the -1 plus DI to the -1. We can rearrange this for DI. DI equals focus to the -1 minus DO to the -1, all to the power of -1. So DI equals negative 7.5 to the -1 minus 25 to the -1, all to the power of -1, which gives us a DI value of negative 5.769 centimeters, which is virtual as we predicted. Now we can use the second equation to solve for HI. HI equals negative DI HO divided by DO. This is negative of negative 5.769 times the height of the object, which is 12, divided by DO, which is 25. This gives us HI equals positive 2.8 centimeters, which is smaller than the 12 centimeter object as predicted, and positive because it's an upright image as predicted. Third example. A 10 centimeter tall object is located at the center of curvature, which is 30 centimeters from the vertex of a concave mirror. What is the magnification? Since the object is located at the center, we know the only possible solution is for the image to be NUR, no change in size, inverted, and real. This means we would expect the magnification to be negative, but since there's no change in size, we would expect this to be equal to 1. Let's calculate the magnification to see if this prediction is correct. We are given the height of the object is 10 centimeters, and the distance of the object to the vertex of the mirror is 30 centimeters. We are also given the location of the center of curvature of the mirror. The focus is always halfway of the center of curvature. This means the focus is half of 30 centimeters, which is 15 centimeters. We need to calculate the magnification, which can be calculated using negative DI over DO. But we don't have DI to do this calculation, so we need to use what we have to find DI. We have focus and DO, which means we can use 1 over F equals 1 over DI plus 1 over DO. This rearranges for DI equals F to the negative 1 minus DO to the negative 1, which gives us a DI value equal to positive 30 centimeters. This is a real image as predicted. Now that we know the DI value, we can calculate the magnification. The magnification is equal to negative DI, which is 30, divided by DO, which is also 30, which gives us a magnification equal to negative 1, which means our image is the same size, inverted, and real. NIR. NUR.